machine learning. Who here haven't heard about machine learning ever? All right, what are you doing here then? Just all right, we all hear about it, like all the time. It's all over the place. We hear about it in the news, we hear about it in conferences, we hear about everywhere. And there's no way around it, and it's kind of part of our daily lives now, and there's a lot of things and we don't even realize it. You know, stuff like smart thermostats that kind of learn all this stuff from you. You've got stuff like your phone that is actually tracking a lot of stuff about you. You might have got some of those notifications on your phone saying, hey, time to leave for work if you don't want to be late. Although you never told your phone at what time you work or where you work. So it kind of just does all of that stuff magically. And less applications are actually asking us for our preferences. It just learns and tries to get all of that stuff on its own, which is kind of cool. But if you start looking at machine learning stuff, there's a lot of information available, and it can seem very intimidating at first. And to be honest, I wrote this talk, or I gave this talk for the first time about 18 months ago, and it was even worse than it is right now. Like, it was basically just academic stuff and papers like published by PhD. And trying to understand what happens there was just like a nightmare. I mean, I have a scientific background. I have a degree in astrophysics, for God's sake. Like, I should be able to understand that stuff, right? But it was so complex. But I really wanted to dig into it. I really wanted to learn a little bit. So I started playing a little bit around, and I managed to get like some very basic algorithms that would kind of work with like very, very simple stuff, like 100 lines of code. And I started to realize, well, you know what? It's actually not that complicated. It's actually very accessible, and there's ways to actually learn how it works. So this is what I want you guys to get out of this session today. I want you guys to understand that it's not that complex. It's not that hard, and don't be intimidated by all those maths and all that stuff related to machine learning. It can actually be easier than you think, and it can actually be a lot of fun too. So hopefully, we'll all have a little bit of fun today. So first thing first, a little bit about me. I am a technical evangelist. I work at Auth0, which means that I get to learn about cool stuff, and I just travel around in conferences, and I share that information. Which is like the best job ever. And at Auth0, we have a platform. It's an identity management as a service. So if you ever need to build a login screen type of thing, just look it up. But this is not what I'm going to talk about today. If you do have a need for any information, whether it's about our platform, machine learning, not that I'm an expert, or astrophysics, hit me up on Twitter. That's the best way to reach me. I am super excited whenever I get a notification on Twitter, so please do so. Also, my boss kind of monitors my Twitter account, so it really looks good for me. I'm from Canada, in case you haven't noticed. I'm very proud, a proud Canadian, and I don't like people to think that I'm an American, so that's why I wear this bright red hoodie. And if you've been to any of my sessions yesterday, you also know that I kind of repeat the same stuff always. All right, so some people were here yesterday. So what are we going to talk about? We're going to talk a little bit about theoretical stuff. What is AI? What is machine learning? I'll cover very quickly deep learning. And it wasn't originally part of the talk, but it's so present out there nowadays that we kind of need to talk a little bit about it. But most of my talk will be focused on simple algorithms. So we'll talk about supervised and unsupervised algorithms, and we'll go through a simple example of a naive Bayes implementation, as well as a genetic algorithm. So AI. If you Google AI, you will get a lot of images like that. So it's usually, most of the time, actually a woman. So I figured that's the I part, or the intelligence part. Usually like cyborg-like with circuits and code. There's always code involved with artificial intelligence. Did you guys notice anything with that code? Anything specific? JavaScript? Yeah, it's the minified version of Bootstrap, actually. But apparently, that's artificial intelligence for you. Artificial intelligence, more seriously though, from Wikipedia, is intelligence exhibited by machines in computer science. The field of AI research defines itself as the study of intelligent agents, so any device that perceives its environment and takes actions to maximize its chances of success at a goal. I have the text in front of me, right? Just so you know. So let's take a little bit more emphasis on this part. So taking actions to maximize the chances at success of a goal. So that's what AI is. So it's a set of rules that we as programmers define to create or to help our software to achieve a goal. So what does this look like in real life? Well, one of the first implementations was Pac-Man. So Pac-Man is very interesting. It was one of the first games that actually had artificial intelligence in it. So I assume that everybody knows Pac-Man, and everybody tried to play, and you kind of have the feeling that the ghosts are actually, trying to catch you. But they're not really doing that. Like, they're just following very, very simple rules, actually. Blinky, the red one, will kind of try to follow you. So no matter where you go, it'll try to to go down that path. Pinky kind of tries to predict your movement. So it will try to take a different path based on where you're looking. And Inky's position is a little weird. It depends on Blinky's position. So let's ignore that one. But the interesting one is Clyde, which is the orange one. And Clyde will try to get as close as Pac-Man as it can. But if it gets within a few number of spaces, it will actually go the opposite direction, and it will get away from Pac-Man. And what this gives us as a user when we try to play, like, you think that Clyde is actually trying to be sneaky and find another way to catch you. But that's not the case. Like, he's just really stupid and getting away. But it's one of the hardest ghosts to wrap your head around, because you actually really need to ignore him. So what this is just a list of very, very simple rules. But all in all, it gives us the impression that they're animated by some kind of force, and they're actually trying to catch us. So artificial intelligence, a bunch of ifs. You'll see that as well in many places. You'll see that in fraud detection for credit cards, for example. So if I start making transactions with my credit card in a foreign country, they'll cancel my credit card, which sucks. It happens a lot. Or spam filters also, just a set of rules, and it just takes care of some of this stuff for you. But we're here for machine learning. So machine learning is the subfield of computer science that gives computer the ability to learn without being explicitly programmed. So that's where it gets really interesting. So the code that you actually write is code for your software to learn how to do something. So you don't give the rules to your computer, you give the rules on how to learn. So it makes it for very interesting programming, very interesting way to think about things. You have to think about, how can I teach something to my computer instead of how can I dictate how to do something. We can see a lot of examples once again. Thermostats. I have the Nest thermostat at home, which is kind of neat. It learns, so Canada can be really hot and really cold. So really cold during winter. So during fall, it asks me, okay, well, start to train me again. So I'll start adjusting the temperature based on what I want it to be like when I get home from work. And eventually it will be smart enough, and it will start the heating before I get home. And same thing during summer, we need AC, so I train it during spring so that it kind of learns what temperature I like. So it's very nice. It really learns all of that stuff. But nobody ever wrote the rule, if summer, then set temperature to blah, blah, blah. So a programmer behind that wrote the rules in order for the thermostat to understand how to train itself. There's a lot of other great examples. We talked about the phones, how they detect your position and where you want to go and stuff like that. I was doing renovations recently at my place, and every Saturday morning I was going to the hardware store. And at one point my phone started telling me, hey, time to go to the hardware store. I was like, no, I'm done, please. There's also Tay. I I think it was mentioned in one of the, was that a keynote or, I'm not sure if people saw that. Does everybody know Tay, the experiment by Microsoft? One or two? So Microsoft came out with this idea that they should build a chatbot, and it was interacting with people on Twitter. And it was kind of a blank slate when they released it. And the goal was for it to learn based on conversation that it was having with humans in order to make sure it could talk in natural language and do all that stuff. So very, very interesting experience. And it was released on March 23rd, 2016. And it was really interesting. So she started tweeting. She would do public tweets as well as direct messages. She was like super happy to meet humans. And not very long after that, it started to be a little bit weird. So that's the next day, the next morning, actually. So March 24th at 9 a.m. I just say to everybody, OK, well, that's still fine. That's a little bit later during the day. That's at 11:41 the same day. So it didn't go very well. So within 24 hours, that chatbot became like a horrible Nazi, misogynistic, like it was just absolutely horrible. The worst thing is that my mom saw that, and she was like, oh my God, computers are taking over the world. Oh, no, Mom. It's those stupid humans again. So what happened there is that we had a software, and it was meant to learn. It was meant to learn based on interactions with humans, but the thing that programmers didn't take into account is that humans can be really stupid, usually much more than machines. So it only learned based on the interactions that it had, and the internet being the internet, people started trolling, people started, doing some weird stuff and telling weird stuff to Tay, and she started to learn. So that's a good lesson, though, if you want to build machine learning. Garbage in, garbage out is really true there. Like, it's very, very important. You have to make sure that the data that comes in and that trains your algorithms is actually valid data, or else you'll end up with stuff like that. Deep learning and big data. So we've all heard about it, right? It's kind of the new cloud. It's like this new buzzword. I actually had a cloud to butt extension on Chrome a few years back, just because I was tired to see a cloud all over the place, and it would replace cloud in every web page by butt, which was so funny. So I've changed it for deep learning, and it changes to butt. So it's just funny. All right. I guess I have a special kind of humor. So with the explosion of big data, we all know that Facebook is especially now, we all know that Facebook is collecting like tons and tons and terabytes of data about each one of us every day. But how do you process all of that data? There's so much things. There's no way somebody can actually go and say, oh yeah, Joel did this today, last year did something else, so he's probably going to want to see that today. No, that doesn't work. There's way too much data. So we needed to come out with new ways to process all of that information. And that's where neural networks come into play. So neural networks are meant to work essentially the same way our brain works. So the way our brain works, well, nobody really knows, but essentially we have neurons, and it makes connections, and there's connections made between all of those neurons. And if you try to train a skill, or if you're trying to learn something, we can see that some of the connections between your neurons are actually getting stronger and stronger. So the messages go faster and faster. So up to a point where things like walking, we don't even think about it. Like, it's right there in our brain. It's built into our neurons. Our connections are made, so we don't need to think about walking anymore. It just magically works. And neural networks kind of work in the same way. So you've got a bunch of layers, and every one of those little nodes, those are entry points. And each one of those nodes performs some sort of operation. And it passes the information to a next layer and so on until you get an output. And it can do stuff like, some of the connections will be trained to detect some shadow patterns, for example, which will pass it over to a next layer that will make some connections to kind of detect facial patterns. And eventually, it will move it to the next level, which will see, well, OK, we've got 2 eyes, 1 nose, 1 mouth, so it's probably a face, right? So it works a little bit like this. It's all about the connections and reinforcing them. There's a lot of frameworks available for that. There's a lot of things. TensorFlow.js just came out like last week or 2 weeks ago. I unfortunately haven't had the chance to play with it. Like, I'm super excited about that, though. So it's machine learning using JavaScript. And whenever I can do something in JavaScript, I always try it. So I really need to try it. So I can't really talk about that. But there's also TensorFlow in Python. And there's a lot of cloud solutions that are available, too. So if you really need a neural network, like a very complex problem that you need to solve, there are great solutions available on the cloud. So Microsoft, Google, pretty much all the giants have their own. But we'll talk about simpler cases. We want to go to the basics so that we can understand and kind of see how things actually work. So in the world of machine learning, there is essentially 2 types of algorithms. The first one is supervised learning. So a supervised learning algorithm is one that you need to train. It requires some feedback in order to make any sense of data. So it starts with no knowledge whatsoever about something. And as you produce data to train it, it will eventually learn and make sense out of that. So you'll see that, well, in the chatbot Tay was a good example of that, of course. And you also see that if you provide bad data, it provides bad inputs. You'll see that mostly in the case of classifiers. So whenever you want to train your machine to understand if something goes in box A or box B, you should use supervised learning. So you'll train it. You'll say, OK, this goes in A, this goes in A, this goes in B, and so on. And eventually, it will kind of be able to make the decision on its own. The next type is unsupervised learning. So unsupervised learning happens when there's no feedback. So it just looks at some data and tries to make sense of it. Or it just tries to make something up. So those are used when there is no real right or bad answer. So I'll come back to that a little bit later. But essentially, it's the type of algorithms that kind of, you've probably all seen if you watch a video on YouTube, and then it suggests another video based on all of your preferences. And then you watch that second video, and it suggests the third one. And then you watch a fourth one. And then all your day just went by, and you've been just watching the next video. Oh, it happened to you. So the video the suggestions that it gives you is not a right or wrong answer. It could give you anything. But it makes predictions based on what it learned from you. All right, so let's look at our first algorithm. Let's introduce the naive-Bayes classifier. So the naive-Bayes classifier is based on Bayes' theorem. So essentially, it's a calculation of a probability of something happening. So you get the probability of B over A times the probability of A divided by B, which gives you something a little bit like this. So probability of B over A times the probability of A over a probability of B, A times B, A plus the probability of B negated A times the probability of negation of 1. So negation, we all know that 1 minus the probability gives you the negation. All right. So of course, if you want to generalize it, and if you have many boxes that you want to train that for, you'll use the product of all the probabilities of A all the way to I divided by the probability, or the product of all the probabilities of A over I plus the probabilities of the negation of all the products. In the end, you get something like that. It always takes a second to sink in that way. All right, I hate maths. I was really bad at maths. I really somehow managed to fake my way into my bachelor's degree in physics, but I don't like it. But there's no way around it. We have to do at least a little bit of maths. So let's look at a simple case. So we all know Forrest Gump. Life is like a box of chocolate. You never know what you're going to get, something like that. So let's say you have a box of chocolate. And let's say you're allergic to nuts, right? And you want to know if the chocolate that you'll pick in that box will actually have nuts in it. And you know, based on previous experience, that round chocolates tend to have a smaller probability of having nuts in them, so about 1 in 4, while square ones have a much higher probability. And dark chocolate tend to have much less nuts in them than milk chocolate or light-colored chocolate, right? So if we translate that into numbers, we want to know if a round light chocolate has nuts in it. So we'll try to translate that into numbers. So 0.25 chance versus 0.75 for having nuts or no nuts. And then you simply do the product of those. Right, so you got 0.225 and 0.075. And you apply the very, very simple version of the Bayes theorem on that. So you can see it. So the probability of having some nuts in a round light chocolate is about 75%. Right, so we can make the decision based on those numbers that there's a 75% chance. So it's up to you as a programmer to say, well, 75 is good enough. So I'll say there are nuts in there. Now, if you have allergy to nuts, don't rely on statistics. When you look at a box of chocolate, just don't take any chances, please. But it kind of helps. So we can kind of figure out that there's a good probability of that being in that box or the other box. So we can see how that will help us with that. So there's a lot of implementations available if you need to build a classifier. And they pretty much always work this way. So you've got your classifier, and you've got two methods. You've got a classify and a categorize. So to your classify function, that's the function that you will train your algorithm with. So you'll give it something and then the box in which it belongs. All right, so we'll look at an example in a few minutes, and we'll try to train our algorithm to learn if text is in French or in English. All right, so we'll pass it a string, and we'll say, well, this is in French. Or we'll pass it another string, and we'll say, this is in English, and so on, until it actually starts to learn. And then the categorize method does the actual prediction. So it will do all of that calculation behind the scenes. So you'll pass it a string, and it will output a probability of being in box A or box B, or in English or French. All right, we're ready. You're excited? Ish. All right. All right, there it is. All right. Is everybody familiar with Tinder? Nobody ever is. Oh, there's one or two. I'm not sure how they are actually still there, because nobody ever says, yeah, I know who that is. All right. Anyways, so we have this interface here, and it doesn't have any knowledge at this point. And if we swipe right, it will learn that this text is in French, and if we swipe left, it will learn that this text is in English. So what we'll do is that we'll just swipe the card here, also French, English. It's a lot of fun, isn't it? Oh, there you go. So already we can see that it detected that this card is in English. So it's already starting to make sense of the data that we feed it with. So if we just continue a little bit, English again. It's an error, English, English, English. Okay, well, all right. So it's kind of detecting that it's in French as well. I could do this all night long or all day long. So just tell me when you want me to stop. It didn't work. All right. Anyways, so you can see that it's fairly easy to train our model to start learning about how things are working and to make sense of, does it go in box A or box B? I thought it was amazing, but anyways, okay. So let's see if I can just get, I'm looking for my cursor right here. Come on over here. Oh, there it is. All right, sorry about that. Okay, so like I said, very, very simple algorithm. We've got two methods here. So we've got our classify function that just takes in some text, and we give it a group, and it will create a dictionary. And I'm sorry, it's not like the cleanest code ever, the most readable code. It gets a little bit hard. But if you want to take some time, it's on GitHub, so you can take a look afterwards. But I tried to do like the simplest implementation I could there. So you pass it some text in a group, and what we do is that we deconstruct that sentence. We break into words, because we're interested in the words. And we'll create a dictionary for all the French words and a dictionary for all the English words. And each time we get an occurrence of each one of those words, we'll increment the counts for that word. Right, so if we get a sentence like machine learning is cool, we have machine learning is cool. 4 words, we deconstruct that, so we add that to our dictionary, we give it a score of 1. If we say intelligence artificielle c'est cool, so we'll have 4 words and we'll put that in the French dictionary and we'll have intelligence artificielle blah, 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 we'll have like those 4 words. But there's also words that are in both dictionaries. So we have cool in English as well as in French. But eventually, as our dictionary gets built up and we increment each time that we encounter those words, either in French or in English, eventually the word cool will have a higher dominance in English. It'll have a higher score. So we can kind of make sense. We can kind of detect that there's a higher probability that this word is in English than in French. But there's still a probability that it's in French too. Now, the categorize function is the ugliest code I've ever wrote. But basically, it does a little bit what we said. So it just takes all of the words, so we pass it a string, it deconstructs the words, takes the count on each side, and it just averages everything out. All right, and that's it. And you've got your first algorithm. Super easy. We've got, 78 lines of code. And there's a few comments in there. Not very useful, but hey. But you've got your first algorithm, very, very simple. You can implement that, and you can start using machine learning right away. All right, so we've got our first algorithm done. Man, I'm having a hard time with my, all right, there it is. All right. Classifiers, and there's also a sentiment analysis, which is often confused for machine learning, but it's actually a set of data that is pre-trained. So it's a classifier, it does the same thing, but it will help you to detect if some text is actually positive or negative. So you can do some research, say you're you're working for a political group or something, and you want to know what people think of you. You can kind of track keywords on Twitter and see if the general opinion is more positive or negative. So you can do some really interesting stuff there, but it's not really machine learning. But it works the exact same way as the classifier we've just seen. The difference is that it has a list of words, which is pre-populated for positive words and negative words, and it kind of gives you a score based on that. So if you ever need to implement that, there's libraries in JavaScript as well as in PHP. And just for fun, I actually wrote a quick script last night when I got back to the hotel, and I just wasn't tired yet. So I wrote a small script where I listen on Twitter for 2 keywords. So I listen for hockey or football, because I want to know which one is more popular. Because I think hockey is much cooler, Sorry. Come on. All right. So what this does is basically it listens on Twitter just through the Stream API, and it looks for all of the keywords, or it looks for 2 keywords. It looks for hockey and football. And for each one of the tweets that come in, it gives it a score. And we just average out those scores to see which one is the coolest. And if we stop it now, because I see it's going lower, so we've got hockey 1.5 and football 0.95. So we can see that with proof that hockey is actually cooler than football. All right. OK, moving on to some interesting stuff. So classifiers, yeah, they're easy. I see that you weren't that impressed. So let's move on with something much, much more interesting. So we'll move into genetic algorithms. All right, genetic algorithms are pretty much the coolest thing ever, in my opinion, at least. Remember that moment when you went to school and the first time you got into school for whatever programming class that you had, and you had to write your first software. And we all wrote the same software, no matter what language it was all the hello world. And you just hit run or whatever it is that you're using, or you open up your browser, and you saw those magic words on the screen. Hello world. How cool was that? And you get super excited. I remember the first time that I had that, I was so happy. And I was trying to show that to people. I was like, look, Mom, I did this. And she's like, yeah, so what? You can use a word processor and just type in hello world. And it's like, it's so hard to try to explain that feeling that you get the first time that you make those magic words appear on the screen. So you can all relate to that, I guess. Genetic algorithm is pretty much the same thing. All right, so if you really want to have some fun, write your own, and you'll be super excited. And you'll want to show it to everybody. And you'll travel the world and go to conferences and go to London and present that stuff to everyone, and nobody's going to care. So if you don't mind, just kind of fake it when I'll show it to you. Thank you. All right, so genetic algorithms are based on basically the theory of evolution of Charles Darwin. So what we do here is that we start by creating a population of random individuals, right? So we just take a bunch of random stuff. And then we set a rule to see who's the fittest. And then we'll just keep like those that are the closest to an actual possible solution. And then we'll also keep just a few random individuals in our population. And we'll kind of just introduce some random mutations in there. And we'll just create children with that new population until we're back to the number of individuals that we originally had. And just magically, we end up with a solution. Right? So random individuals, we keep some random individuals, we'll introduce random mutations, we randomly create children, and magically, we have a solution. How cool is that? So what is it used for? It's used to help, it's useful for cases where, like I said, we don't have a valid solution or not, and when we need a computer to think outside of the box for us. So you want to build a bike. You want it to be the most solid as possible. You want your bike to resist any collision with somebody opening its door, right? You want it to be super solid. So your fittest criteria will be how solid it is. So you'll create a bunch of random stuff, random bike models, and you'll all test them to see how solid it is. And then you'll just continue to create new populations, new generations, until you find something that you think is acceptable. So it will kind of give you things that you might not have think about, something like that, or like this. You know, it's not bike models that we originally would have thought. We tend to think of the things the way they're already built. Say you want to build the lightest possible one for a drone, for example. So you see that some of those are more fatter. They would be solid, but they're way too heavy. So you know, the computer will come out with all kinds of different ways to generate all of that stuff. Time for the demo. All right, so what I did here, is that I wanted to create an algorithm that will find an array of 4 numbers for which the sum is 200. All right? So I'll just generate a bunch of random, sorry, an individual in this case is an array of 4 numbers. So I'll create 200 of them, just all random numbers, and then I'll introduce and I'll start doing the cycle. So what your code actually ends up looking like, not this one, sorry, that you've got an evolve function, and evolve will do exactly that. So it will start by creating a new population. So it will look through all of the solutions that it generated. It will keep those that are the closest to what I'm trying to get. So I'm trying to get the 4 numbers which sum up to 200, so those that are closest to that. It will extract them, start to create a new population with that. And then it will introduce a few random elements from the previous population into there, so we're kind of growing that population. And then we mutate some of the elements. So I'll just take that new population, and I'll give it a chance of each one of those of just being randomly mutated. Right? So I'll just introduce new random numbers somewhere in there. And then we want to get back to the same original size, population size that we had, so we'll create children with this new population. So we'll take randomly 2 of those elements that are already in that population, and we'll create a new children with that. So I'll take the first 2 numbers and the last 2 numbers, and that will be a children. So we want your children to inherit properties from the parents. And then you just run this over and over and over and over and over, and eventually you find a solution. So what does this look like in code? Yeah, of course you're there. All right, I'll make it really big, because it's so cool. All right, are you ready? Go. Thank you. All right, so we've got a solution, and we've got 4 random numbers that actually sum up to 200, or very close to 200. Maybe not exactly, but it's kind of interesting. And you see that we found those 4 random numbers. It took 12,610 generations. If we run it again, 27,000 generations, and it comes up with a totally new solution. So that's what I meant when I said, it doesn't really matter what the solution is at this point. The only thing that I want is 4 numbers that actually match that. So that's what we get. All right. I get it. So I gave you something a little bit more interesting to see. When I said there's a lot of academic stuff that is available online, this is one of those. So it's a study that was done by some students, and essentially they're using a genetic algorithm here to teach a model how to walk. So the model has no knowledge whatsoever on how to walk. They just said, well, you've got muscles here, muscles flex this way, you've got joints. And then they created different models, different sizes. And they just ran the simulation over and over and over. And the fittest in this case was the one that could stay the straightest and move the further away possible. So what we got after a few generations, I say we, I didn't participate in that whatsoever, but what they got after a few generations, we'll just let it run a little bit, was walking creatures something like this. And like I said, different models, different type of things. And it's actually interesting because you can see different, how those models try to learn. So that's how it was trained. As you can see, after a few hundred generations, it gets better and better. I like that one. All right, ciao. All right, so it was a very interesting, cool. It's an interesting video as well. The link is in my slides if you want to watch all of this. But essentially, yeah, they taught it how to learn different speeds, different type of things. Of course, us being humans, we started throwing things at it. And at the different models, different slopes. We tried to steer it. We tried to throw things at it in a slope. All right. Okay. So that's what you get. Okay. Like I said, you need to introduce random mutations as well, because at some point, your model might start to learn things in a different way or in a different pattern that is not the best one. And it will kind of try to still steer in that direction. So you need to, I like that one. So, so you need to tell your algorithm at one point, okay, this is not going to work. So you need to steer it in another direction. So that's why you want to introduce random mutations. By introducing those random mutations, it might find a better solution, one where it would actually walk straight and walk in a better way. So that's why you have all of that random stuff going on. All right, so the code, we've all seen it. So what did we learn? Well, machine learning and artificial intelligence, I don't like how people use those terms interchangeably. So now you know what's the difference, and you can correct all the people with me. Big data and deep learning, if you want to use it, by all means, use one of the cloud solutions. There are so many out there that are available. Supervised and unsupervised, and you all now know how to make your own naive-based classifiers, as well as genetic algorithms. And I'm sure you will all do one now, of course. If you do so, tweet me. I want to know how that goes. I want to know how excited you are. And hopefully, you won't be intimidated by machine learning anymore. Thank you. Do we have some time for a question? I'm not sure which time we're supposed to stop. Let's just stop it right here. If you have any questions, come and find me. Come and talk to me. I'm easy to find. I have a bright red hoodie. So by all means, I'll be more than happy to chat with you. So thank you very much.